Hello and welcome back. This is the fourth lecture slideshow for Philosophy 125, the Philosophy of Science. In whom do we trust? Our own limited personal experiences or the collective controlled experiences of scientists who actively try to reduce bias and error? What standards shall we use to judge claims about our world? So this is our issue for week 4. What standards and hierarchies of evidence do scientists use? These slides cover approximately the fourth week of the course. For this set of slides, read Chapter 1 of the Akasha text. We are still covering material from Handout 1, Sections 6 through 15, especially the parts where I discuss evidence standards. Before viewing this entire lecture, be sure to watch the following 3 healthcare triage videos by Dr. Aaron Carroll. These short, excellent videos introduce you to the highest-ranked forms of scientific evidence using examples. They move fast, so I have to watch these more than once. Dr. Carroll is a relevant expert on the subjects of his videos. He conducts research himself and reviews the works of others within his area of expertise. I include a screenshot of his bio page at the New York Times, and the following slide lists the YouTube titles on the next page. I include links to these videos within the blog page. There will be more videos made by Carroll and others throughout the course I'll ask you to look at. Here are URLs for the 3 Aaron Carroll videos. Search on the titles if necessary. You need to understand what randomized controlled trials are, systematic reviews, and meta-analyses. You should understand these after watching these videos. Let's review a little bit of what I discussed last week. People such as scientists and physicians want to go beyond mere observations of correlations between good and bad outcomes and whatever curious facts we notice prior to those outcomes. Correlations might be illusory or accidental. Correlations, when real, between specific factors may also occur because of some more remote common factor beyond the factors noticed, or they might be explained by some as yet unimagined factors. Overlooking alternative explanations of correlations, associations happens when we are hasty, lazy, or persuaded by popular opinion. In short, scientists and physicians, and not only these people, want peer-reviewed, randomized controlled trials to demonstrate actual cause and effect connections between the factors and outcomes we think we see. We can't rely on our own subjective experiences. We need to get systematic and more objective. To review, here are 5 issues with herbals revealed in the video Alternative Fix. There's a lack of scientific evidence of safety and effectiveness for these treatments, for these supplements. There's a lack of regulatory oversight. There's a lack of quality control. There's a lack of knowledge about herb-drug interactions by patients and healthcare providers. For example, serious cardiovascular effects are not uncommon in people who use these. There's also this underreporting of adverse drug reactions. Here I list some of the drug-herbal interactions people need to be aware of when they take herbal supplements. And since these interactions are, in some cases, serious, we can't just presume that the fact that these supplements are herbal makes them effective or safe. Here are some possible side effects of herbal supplements. Alternative medicine is too often unsubstantiated. Alternative medicine claims are often based only on anecdote, personal stories, or folklore, and used instead of tried and successful therapies. Alternative medicine is too often untested. Such claims rarely get checked under adequately controlled circumstances. Stories with happy outcomes are not enough. All therapies require clinical trials. I recommend looking at the website clinicaltrials.gov and its glossary of terms at the National Institutes of Health to see what exactly these look like, how they are registered, how we have to share the results of these trials. In fact, the government is making it a precondition of funding that you share your results, be they positive or negative. Alternative medicine therapies don't control for placebo effects, that is, any physical or emotional changes occurring after a substance is taken or administered that aren't the result of any special property of the substance itself. Such changes may be beneficial, which reflect the expectations of the participant and often the expectations of the person giving the substance. And finally, alternative medicine is too often biased. Bias is always an issue, but it's especially the case with alternative medicine. In many cases and countries, only the positive results of these tests get reported. Confirmations get reported. Negations do not. Why can't we conclude that observed correlations between variables imply causal connections? Because too often correlations are coincidental, or some other cause or multiple causes may underlie and explain both of the things correlated. Scientists test causal claims by finding correlations first and only then trying to explain them. Evidence for a cause and effect claim requires a correlation, a regular association between two variables or events or kinds of events. For example, taking a vitamin C supplement and having fewer colds. Between owning a gun and committing suicide, between being married and being happy, between the unemployment rate and the crime rate. Let me say more about what a correlation is. When two sets of data are factors, let me say a little bit more about what correlation is. When two factors or sets of data are strongly linked together, that is, they appear to occur near each other in space and time, we say they have a high correlation. We can't yet conclude there's a connection in any way such that the first causes the second. Correlation is positive when the values increase together, and a correlation is negative when one value decreases as the other increases. A correlation is assumed to be linear following a line. That is, we can draw a line using a linear regression, and we assign values to the correlation. Some number between -1 and +1, where 1 is a perfect positive correlation, that is, when the one increases in frequency in the population, so too does the other. So if we look at the frequency of people owning guns in a population, the number of guns owned in a community, we also notice an increase in the number of suicides by gun in that community. Again, no necessary connection, just noticing the trends. The increases in frequency track one another. 0 is no correlation, that is, no correlation observed. The values don't seem to be linked at all. And a -1 is a perfect negative correlation where when the one increases, the other one decreases. It's not about going negative, it's about when they go in different directions. On a chart, we can plot on one axis the number of cancer cases versus the number of cell phone users on the other axis. We see a positive correlation. That is, as the incidence of total cancer cases increases, we notice as well that there has been an increase in the number of cell phone users. Should we conclude that X causes Y or that Y causes X? Both? Neither? Answer: nope. We have insufficient evidence to say without a controlled experiment that clearly induces the effect in question. These are the sorts of experiments where we actually make an outcome happen. A standard of evidence helps us judge the value of evidence. We need these. Idealized lists or diagrams represent the top-down relations between kinds of evidence from the best, for example, systematic reviews of peer-reviewed randomized controlled trials, to the least credible, for instance, personal opinions. In the next few slides, I distinguish between general standards and science-specific standards, where the science-specific standards are just those represented in the hierarchy of evidence diagram I'm going to use. General standards apply in multiple domains, including philosophy, science, law, journalism, from which we derive and evaluate evidence. Notice that the scientific standards, the hierarchy, are a subset of general standards. Notice that the scientific standards, the hierarchy, are a subset of the general standards. Let's look at some general standards of evidence ranked. Highest standard, the philosopher's standard, is the beyond the shadow of a doubt standard. This is the attitude we have when we believe it's impossible to doubt a proposition, a specific proposition P. For instance, suppose the proposition is that I exist. That's impossible to doubt. At least I can't possibly doubt it. Another example, your proposition might be that there's a world outside of me. There's an external world. I can't doubt that. And so the attitude I have towards the claim that there is an external world independently of my own existence is that I can't possibly doubt it. So that satisfies the beyond the shadow of a doubt standard. Second, beyond reasonable doubt. You've heard this in courts of law. This is the attitude you have when you have no plausible reason to believe not P, where P is, for instance, that a person is guilty of a crime. If there is real doubt after careful and impartial consideration of all evidence or a lack of evidence, then this level of proof has not been met. So if we fail to defeat doubt about a person's guilt, then we judge them innocent. We might be mistaken, but again, the standard is about our attitude with respect to the evidence, our attitude about a specific proposition, namely the person's guilt or innocence. The next standard is the clear and convincing evidence standard, where your proposition is believed to be substantially more probable, substantially more likely true than not. And this is a standard that's met in controlled experiments, where we try to control for as many variables, confounders, biases, measurement errors as possible, such as we have in peer-reviewed randomized controlled trials, which I'll say a whole lot more about. I'll call this the highest standard in science. Next is the preponderance of evidence standard, also used in the law and especially science. This is the idea that P is more likely to be true than not true. That is, there is a greater than 50% probability that P is true. And this is the standard we meet when we do observational studies, which show us correlations between, say, changes in diet and changes in health outcomes. This is the sort of evidence we need to get correlations. I'll call it the fifth standard, the fifth on my list of ranked standards. I'll call this substantial evidence. That is, there is more than a scintilla of evidence, but less than a preponderance of evidence. And this consists of any such relevant evidence as a reasonable person would accept as adequate to support a conclusion. This is where we start to use something called an evidence hierarchy, an evidence pyramid. I'll talk about the evidence pyramid next. So substantial evidence is below the standard of preponderance of evidence. Preponderance of evidence is below the standard of clear and convincing evidence. Clear and convincing evidence is below the standard of beyond reasonable doubt. The last standard I'll talk about here is the one where people say, well, there's some evidence to suggest a connection between X and Y. Some evidence. This is a bare minimum. It does not consider conflicting evidence. This is the level of it's possible or it's plausible that there's a connection. For instance, climate change deniers reside here. It's possible that climate change isn't real and that scientists are mistaken, or that there's this conspiracy, or that we're misreading evidence, etc. So I'm going to call some evidence that's consistent with the claims someone makes about the world. I'll call that the lowest standard. You always have to have some evidence. When somebody says there's some evidence for something, you really should read it as there's not enough evidence to satisfy the higher standards, such as substantial, preponderance, or clear and convincing evidence. Okay, my list and ranking of standards simplifies. It's not perfect. But levels 3 to 5 are what science uses. So let's strip away 1, 2, and 6 and focus on these. Here is a diagram representing a hierarchy of evidence specific to science. If you like, this hierarchy fits into that category, substantial evidence. Briefly, at the top of the pyramid is the best kind of scientific evidence available, that provided by systematic reviews or a meta-analysis. At the second level are the randomized controlled double-blind studies. I call these also peer-reviewed because fellow experts have to review your work, approve of your work before it gets published, before you get further funding. Below that are cohort studies, case control studies, case series, case reports. I'll call those observational studies where people make observations, they describe what they see. Perhaps they use some statistics to get averages, but they are unable at that level to establish cause and effect relations at best, and yet this is very useful. They provide correlations, and from correlations we can design further studies where we use randomized controlled trials to test possible causal connections. Below these we have the realm of editorials, ideas, opinions, and these would be those of relevant experts, not just regular people. And below this we'll get animal research and test tube research. There's lots of animal research and test tube research. It's better than ordinary people watching events and trying to tell stories about what they think causes those events. Animal research is prior to research in humans, for instance, case series, case reports, case control studies. And while we use animals in research and randomized controlled trials and in systematic reviews as well, animal research, because it's about animals and not yet people, isn't regarded as good as using people. Nevertheless, if something is not on this hierarchy, if something is not at least animal research or test tube research, scientists really don't take it seriously. So anecdotes, personal stories, they're not even on the list. There are other ways to represent the relative ranking of evidence. This rough guide diagram here that I linked to in handout 1 is another representation of an evidence hierarchy, which puts the best evidence at the bottom of its diagram. You can put it at the bottom or the top. On this, you go down the list. As you go down, you get an increasing strength of evidence. And here are some examples. You can't read it on the slide, but go to the hyperlink on handout 1 and you can see more, and you can also see examples. I include in handout 1 links to examples online of each of these sorts of evidence and some studies that satisfy those. Biases and error occur at all levels, but they are better controlled for at the higher levels, and they're way better than people just reporting what they take to be evidence based on their personal experiences. We're going to focus on the top 2 regions of the evidence pyramid, which covers the top 3 most important kinds of evidence. I'll discuss those in this slideshow. Those are peer-reviewed randomized controlled trials. These are tests that pass rigorous review by experts. We'll talk about systematic reviews and meta-analyses. Again, if you have not watched the 3 healthcare triage videos by Aaron Carroll, which I referred to you to at the outset of this lecture, please do so now, or you will not be understanding what I tell you. I go into more detail about lower levels of the evidence pyramid in handout 1. I provide hyperlinks to examples on the internet of each within handout 1 as well. Let's look at a randomized controlled trial. That is, studies that are typically reviewed by expert peers. You have 2 groups, a treatment group and a control group. The treatment group receives the treatment under investigation, the one you suspect might have a role in the positive outcomes observed in previous studies finding correlations or associations. You also have a control group, which receives either no treatment or some standard default treatment. This would be a group, for instance, that might receive a placebo. We have random assignment to all groups, which reduces the risk of bias and increases the probability that differences between the groups can be attributed to the treatment. Again, random assignment. What's that? To say a person is randomly assigned to a group is to say that everybody has an equal chance of being assigned to either group, the control or the experimental, the treatment or the control. A control group, again, allows comparison of the treatment with alternatives. For instance, the claim that chiropractic cures 40% of cases of lower back pain tells us very little unless we also know how many cases get better on their own. And we compare the results between the 2 groups. Systematic reviews and meta-analyses. These can occur together or separately. They're different. In each case, you have research teams in different locations. They examine the same questions. Then their results are pooled and analyzed by other researchers. They're combined. Systematic reviews survey and summarize all relevant studies at the highest level of evidence, such as all peer-reviewed randomized controlled trials that test the same specific hypothesis. Meta-analyses combine all similar studies statistically and analyze results as one study. What's the difference between a systematic review and a meta-analysis? A systematic review is a comprehensive, explicit way of interrogating, asking questions of peer-reviewed scientific literature for an answer to a specific question. It involves several steps, including asking an answerable question, identifying one or more databases to search, developing a clear search strategy, selecting titles, abstracts, manuscripts based on explicit inclusion and exclusion criteria, and abstracting data in a standardized format. A meta-analysis is a statistical approach to combine data derived from a systematic review. Therefore, every meta-analysis should be based on some sort of literature or a systematic review. But not every systematic review leads to a meta-analysis. The best reviews analyze peer-reviewed, randomized controlled trials. Let's talk about an example of systematic reviews and a meta-analysis combined. Here's a study from 2012 in the Journal of the American Medical Association entitled Association Between Omega-3 Fatty Acid Supplementation and Risk of Major Cardiovascular Disease Events, a systematic review and meta-analysis. Here's the question: does fish oil consumption lower all-cause mortality, cardiac death, sudden death, myocardial infarction, and stroke? Early studies suggested that fish oil has major cardiovascular benefits, but later research found little effect. Fish oil, omega-3 fatty acid consumption, is among the top 10 most common natural products consumed by adults. Among adults who use natural supplements, over 30% consume fish oil. Now, on the next slide, I want you to notice what happens to the alleged effect of fish oil consumption on all-cause mortality when the overall sample size of subsequent and larger studies is pooled into a statistical analysis. What is all-cause mortality? That's the death rate from all causes of death for a population in a given time period. Here's the point. The alleged correlation between consuming fish oil supplements and decreases in mortality rates actually diminishes to an insignificant level when you add more data. So where earlier studies, smaller studies, found a correlation, found an association between consuming fish oil and reducing mortality rates, adding more studies reveals that the link is illusory. No correlation, no cause. If you can't find a correlation, you have no grounds for saying there is a causal connection. Here's a figure 5, from this published study on the cumulative meta-analysis of omega-3 supplements on all-cause mortality. You'll notice at the top mentions a study from 1995, and at the bottom it mentions a study from 2012. And you'll notice the cumulative sample size increases because each sample is added to the other. This is what a meta-analysis systematic review does. In the middle, you've got your relative risk. This is the risk associated with consumption of omega-3 fatty acids. All right, so we've got small studies on down to big studies. What you need to look at is the relative risk number, and this is reported between 0.5 and 2.0. Notice that the difference between groups disappears as sample size increases. Look at that relative risk number. A relative risk of 1 means there is no difference in risk between the two groups. So you'll notice early studies found that the relative risk was below 1, which means it looked like there was a favorable response to omega-3 fatty acid supplements. That is, it looked like it actually had some effect on lowering all-cause mortality. But the more studies we did, the more samples we added, that number, those averages, converges on 1, which means there's really no difference between taking the supplement and not taking the supplement. Let's be clear. What hypotheses are under consideration here? There is a causal hypothesis, a cause-effect claim. Fish oil consumption lowers all-cause mortality, cardiac death, sudden death, myocardial infarction, and stroke. This is where people were saying things like, and they still do, that fish oil lowers your risk of death to any of these things, these known causes of death. There is also, prior to the causal hypothesis, there was the conclusion that there appears to be a connection, that is, that there is a correlation. Fish oil consumption associates with lower all-cause mortality, cardiac death, sudden death, myocardial infarction, and stroke. You're able to say there's an association because it looks like there is. That's all, an association in our perceptions. Again, association, link, these are not necessarily connections, not necessarily causal connections. You need a correlation to go ahead and say there's a causal connection. Again, after looking at these studies over time, collecting their results, the correlation actually disappeared. When reviewing studies, you need to state precisely at least one null hypothesis the study is powered to test and its alternative. I want to say more about the null hypothesis and the alternative hypothesis. These are going to be the rival claims which account for data, observations under controlled circumstances. Does fish oil consumption actually lower all-cause mortality, cardiac death, sudden death, myocardial infarction, and stroke? The table, figure 5 on a previous slide, shows the results of research on omega-3 supplements over the past 17 years, where a small relative risk number indicates a beneficial effect and 1 indicates no effect. Again, a relative risk of 1 means there's no difference in risk between the two groups. Below 1 means there's a difference, and above 1 means there's a difference. If you see below 1, you start to think maybe there is a positive effect of the fish oil. If you see above 1, that would be what we would see if there were a measurable difference in effect. For instance, that would be what we would see if we thought the fish oil had a negative effect on all-cause mortality. So a relative risk above 1 would suggest that taking fish oil increases your all-cause mortality. So as far as I know, no studies found that. My point here is that we're getting closer to a relative risk of 1, meaning that there's really no difference in the risk of death before or after or independently of consuming fish oil. It's the same in the groups that consume the fish oil as it is in the groups that do not. So here's the lesson. Don't believe everything you read, especially if there is only one study or a study has a very small sample size. It's possible fish oil has a slight beneficial effect, but it is unlikely after all of these studies, and we should not believe it given insufficient evidence. Early studies are useful. They're pilot studies. If they get positive results, this is a good reason to have further, larger, more carefully controlled studies. There's no reason to move on if you don't see an initial correlation. Again, this hierarchy of evidence I'm showing you here is a set of standards, a ranking of studies which fits into the more general standards of evidence I've presented to you already. Let me summarize the biggest issues with the rest of the hierarchy of evidence pyramid below peer-reviewed randomized controlled trials. There are very few systematic reviews and meta-analyses since there are not that many peer-reviewed randomized controlled trials, which are expensive, time and resource consuming, hyper-focused, and slow to process. There are lots of observational studies, that is, cohort studies, case studies, etc. This is good, but at best, such studies may find correlations between factors and variables. They never demonstrate that one factor causes another. At best, they find correlations and suggest hypotheses worth testing further with PRCTs. Most nutritional studies are observational. They cannot show actual connections without inducing the effect using a PRCT. So if we want to establish a causal connection, we need PRCTs. This is the biggest problem with alternative medicine claims. At best, positive outcomes suggest that herbals or supplements might be causing people to feel better, but they might also have no effect. So we need to do PRCTs. Some definitions of the terms I've been using throughout. Hypothesis. A hypothesis is a supposition about a specific issue, an assumption. A null hypothesis. This is a kind of hypothesis where the assumption is that there is no significant association between two or more variables. Randomized controlled trial studies are usually powered to reject the null. I have examples I'll show you shortly. Alternative hypothesis. This is going to be the opposite of the null. That is, that there is some sort of association. A statistically significant result. This is the idea that the likelihood that an observed relationship between two or more variables is affected by something other than chance. The null hypothesis, H sub 0, is the baseline hypothesis most investigators accept already about, say, the effectiveness of a supplement or drug. I call it the default hypothesis. It's the idea that when someone tells us A causes B, first we think, well, maybe, maybe not. I'm not going to think that A causes B until I have a reason to believe it. So the null hypothesis is that A does not cause B. The alternative is that A does cause B. The null hypothesis is that hypothesis that whatever you are testing has no effect, no correlation, no association with the outcomes you observe. By default, for any new supplement, prior to testing, we say that eating a specific herbal supplement S does not lower the risk of heart attack significantly. We aren't sure one way or the other. Our minds are not closed. So we have to start by being skeptical. Usually we start by assuming that a null hypothesis is true and then reject it when the alternative hypothesis is more likely. We power a study, we design a study to show that the null hypothesis is false. This enables us to accept, temporarily, that the correlation a person observes, a study observes, is real. Again, contrasting null versus alternative hypothesis testing. The alternative hypothesis, call it H1, H2, would be that eating the herbal supplement S does lower the risk of heart attack significantly. So investigators do randomized controlled trials powerfully enough to reject the null, just in case, in fact, the null is wrong. We reject the null hypothesis when, for example, a meta-analysis finds that, in fact, the null is false. In this case, say, when statistically significant data support strongly the claim that herbal supplement S actually does lower the risk of heart attack. Usually we start by assuming that a null hypothesis is true. That is, that the, say, herbal supplement does not lower the risk of heart attack significantly. And then we reject it when the alternative hypothesis is more likely, when we do a randomized controlled trial and actually see a difference between the experimental group and the control group. The experimental group gets the supplement, the control group does not. Here is how to take a claim and generate testable rival hypotheses about it. Suppose someone says that children of traditional marriages suffer fewer mental health problems. Well, such children do or they don't have fewer mental health problems. But we have no reason yet to just believe it already without looking at all relevant evidence. We begin by presuming it's not true. By presuming it's not true that children of traditional marriages suffer fewer mental health problems. It might be true, sure, but again, this is what we need to check. Our null hypothesis then is just the denial of the original claim. The original claim being children of traditional marriages suffer fewer mental health problems. By default, we accept the null hypothesis and reject it given evidence to the contrary. This is because it is much easier to show that some claims are false than it is to show that they are true. Continuing, how to take a claim and generate testable rival hypotheses about it. The null hypothesis is this. Children of traditional marriages do not suffer fewer mental health problems. We then set up a test that can disprove it. We look for an actual difference in mental health issues between the children of non-traditional marriages versus children of traditional marriages. If we see a real difference, the null gets rejected, and we accept the original or alternative hypothesis. The null is the alternative to our default belief that children of traditional marriages do not suffer fewer mental health problems. In this case, the null and the alternative are opposites. We accept the alternative only if we find evidence compels us to reject the null. None of this proves that either hypothesis is ultimately true. This is not how it works. It only shows that one hypothesis better describes what we observe than the other. All we reject or accept is a correlation. Observing an association or link is a good reason to reject the null. I just outlined a simplified way of framing null and alternative hypotheses. However, in science, there are way more complex statistical ways of doing this that are beyond the scope of this course. I encourage you to Google hypothesis testing for further details and scientific examples. Do this, really. You should not think you understand this until you at least read the pretty good Wikipedia article on this. I recommend reading the first part of this Wikipedia page on statistical hypothesis testing. Go to Wikipedia, type the phrase statistical hypothesis testing. Look especially at sections 1 through 3, and I want you to review the examples. There are 4, 5, 6 of those. I realize this method of hypothesis testing is probably new to you, or is very different than the poor introduction we get to hypothesis testing in high school. But this is the basic procedure scientists go through when they are serious about testing any interesting or informative claim about the real world. Let's review the methods. Suppose we want to test these claims. Here are 4. Children of traditional marriages suffer fewer mental health problems. Number 2, abstinence counseling is an effective means of preventing teen pregnancy. Number 3, intellectual differences between the sexes are due to genetic differences. Number 4, climate change is a hoax perpetrated by the Chinese government. Here is how we explicitly frame the null hypothesis for each of the 4 prior examples. They're all on one slide now. These are all the null hypothesis versions. Children of traditional marriages do not suffer fewer mental health problems. Abstinence counseling is not an effective means of preventing teen pregnancy. Intellectual differences between the sexes are not due to genetic differences. Climate change is a hoax not perpetrated by the Chinese government. Well, these are easier to test. You would show that each of these claims, any of these claims, is false, just in case you actually saw a difference. Let's say a little bit here about some of the errors in hypothesis testing. In published studies, we look for the p-value in statistical results reported by researchers. A p-value less than 5% is a typical significance level or threshold for rejecting a null hypothesis. Nevertheless, errors in sampling or interpretation occur. Perhaps you've heard of these, the type 1 versus the type 2 error. In the type 1 error, you reject the null hypothesis when the null is actually true. It's a mistake, it's an error. For example, there really is no difference association correlation overall, but data seem to show it. So you're rejecting the null mistakenly when you should actually accept it. A type 2 error is when you accept or fail to reject the null when the null is actually false. For example, there really is a difference, but data do not show it. I'll give you some examples, but let's take a closer look at what this means exactly, what hypothesis testing errors are. So on the one side, we have what we measure or we perceive or what we seem to see. And on the other side, we have reality. So suppose what we perceive to be true is really true, then our hypothesis is correct. Suppose what we do not perceive turns out in reality is not the case. The reason we don't perceive it is because there's no connection. For instance, suppose we fail to see a difference between people who take fish oil supplements and people who do not with respect to mortality rates. We would be correct accepting the alternative hypothesis only if it were the case that we actually had mortality rates decrease when people consumed fish oil. Let's talk about type 1 and type 2 errors. When what you perceive to be the case, when what you perceive is true actually is not, we're going to call that a type 1 error. When what you perceive not to be the case, when you say you don't see an association, and in fact there is an association, in reality there's an association, that would be a type 2 error. A little more detail about the p-value here. The p-value, or calculated probability, is the probability of finding the observed results when the null hypothesis is true. I'm never going to ask you to calculate or assess these in the course. I do want you to be aware of what these are. You're going to see them in the papers I ask you to read. For example, in a court of law, the null hypothesis is the accused did not commit the crime. The null hypothesis expresses the status quo, the baseline set of beliefs, the current state of affairs, the existing more or less uncontested way things are. It's basically the default presumption that a good test could cause you to reject. By default, we assume a person is innocent, and we defeat the presumption of innocence. when we introduce overwhelming evidence that they've done a crime. Evidence presented by the prosecution could defeat the null hypothesis. If it doesn't, then the null remains the baseline assumption. We presume the person's guilty. We presume the person is innocent, not guilty. Okay, some examples. In general, usually, the null hypothesis is what a study or test is powered to reject. I mentioned two types of errors here. Type 1. Type 1 would be a false positive. Type 2 is a false negative. On the left, you've got a man being diagnosed by a physician. Physician says, you are pregnant, but it's a man. So whatever led him to believe he's pregnant, however much the test indicates pregnancy in women, it can't work on men. So this would be a positive result, a result that would make him think he's pregnant, but it's actually false. So it's a false positive, it's a type 1 error. In his case, the error the physician made is that he rejected mistakenly the null hypothesis. On the right, you have a woman being diagnosed by a physician as not pregnant, and yet looking at the image, you can tell, well, she really is. So if you say she isn't, and she really is, that's a negative result, which is false, a false negative, a type 2 error. We assume someone is not pregnant by default, and we test for signs of pregnancy. PRCTs test hypotheses, and so they help us reject a null hypothesis and consider an alternative. By default, we assume people are not pregnant, male or female. Now, if you've got a male, it takes a lot. It would take, I don't know what, to defeat the hypothesis that he's not pregnant. I suppose, if it turns out he was not a genetic male. For instance, some males with testicular cancer produced a hormone that indicates pregnancy. It's a hormone that's also produced in pregnancy. This test looks positive. However, it could be mistaken. Consider the urine dipstick test. This test looks positive. However, it could be mistaken. That is, a false positive. On the top, you've got the 2 red bars. According to the test kit, it says 2 red bars indicates probably pregnant. 1 bar would be not pregnant. So it looks positive, however, it could be mistaken. If it is mistaken and it says a person's pregnant, that's a false positive. Look at the test on the bottom. It looks negative. It's got the 1 bar. This test looks negative, but it could be a false negative. Now, of course, you'd follow these dipstick tests with better tests, more reliable tests in a clinical setting. Right now, if a test says negative, you're not pregnant, you could still be pregnant. Now, if you accept that you're not pregnant and you're pregnant, that would be a false negative. Let me say something about how those tests work. I mentioned HCG. HCG is human chorionic gonadotropin. It's a hormone produced by the placenta after a fertilized egg implants in the uterus. The presence of HCG is detected in some pregnancy tests, for example, HCG pregnancy strip tests. But some cancerous tumors produce this hormone also. Therefore, elevated levels measured when the patient is not pregnant may lead to a cancer diagnosis, and if high enough, paraneoplastic syndromes. Look it up. However, it's not known whether this production is a contributing cause or an effect of carcinogenesis. The pituitary analog of human chorionic gonadotropin, known as luteinizing hormone, is produced in the pituitary gland of males and females of all ages. The point: males and females can have a high HCG. Only in females can you consider perhaps they're pregnant, not in males. If you were to say a male is pregnant with a high HCG, you would be committing a false positive. You're saying he's pregnant, but that's false. Okay, evidence, good or bad, is relevant, useful information. Let's talk about evidence. How exactly does evidence support or undermine claims? Evidence is relevant, useful information. Let's start there. Evidence is anything presented in support of or counter to a proposition. The proposition can be a hypothesis in science, a diagnosis in medicine, or a fact or point in question in a legal investigation. Evidence based upon scientific measurement, controlled observation, needs to be both reliable and valid. What exactly do these terms mean? They don't mean in science what they mean in ordinary language, so I need to draw the distinctions. Evidence must be accurate and reliable. First, We need to distinguish three senses of the term valid. Second, we distinguish valid in the scientific sense. Evidence must be accurate and reliable. First, we need to distinguish three senses of the term valid. Second, we distinguish valid in the scientific sense from reliable in the scientific sense. Two terms, valid and reliable. Next, we distinguish two senses of precise used in science and consider tests and examples of these concepts. Why bother with these semantical distinctions? Because the meanings of these terms matter in judgments we must make about the quality of evidence for or against accepting a proposition. Warning: the term valid has at least three senses and they are often confused. The first sense: valid can be said of a claim or perspective to mean good or true or credible or acceptable. This is how the term valid functions in ordinary language, which is fine. There's another sense. It's said of an argument to mean it is impossible for the conclusion of that argument to be false, given that all of its assumptions are true. Now, this comes from logic, philosophy. This is called the truth-preserving form sense of valid. Very different than the first sense. The third sense is the one we're going to see used in science. I'll talk about that second sentence some more when I introduce logic, basic logic. The third sense of valid is when we say of a process or test or observation that it produces consistent or repeatable results. Scientists, philosophers, but not regular people tend to use the term in senses 2 and 3. But sometimes it's not easy to tell which one is in use. I'm going to focus now on the scientific sense of these terms. Again, reliable does not mean valid. Reliability of measurement or a process or a test is a way of describing precision or consistency in results, not exactness. Validity is a way to describe accuracy also. A valid test is both reliable and accurate. So if a test is valid, it's reliable and accurate. For example, a calibrated scale that reports your correct weight every time you weigh yourself is valid because it is both accurate and reliable. It tells the truth over and over consistently. In science, to say a test is valid is to say it's reliable. Valid means reliable and accurate. There can be reliability without validity. What's that? There can't be validity without reliability. For example, a broken scale could say you are 150 pounds every time you weigh yourself, but it's still wrong. You weigh 175, the scale's broken. So it's reliable, but it's not valid. C, because it's consistent, but not accurate. For it to be valid, it's going to be both reliable and accurate. The scale is reliable, but not valid because it is not accurate. All it takes to lose validity of a test is to compromise reliability, which is consistency, or accuracy, which is truth. Warning: the term precise has two senses, often confused. We can say a claim is precise to mean specific or exact. The claim may or may not be true in ordinary language. In philosophy, this is how we speak. Eating garlic lowers cholesterol is imprecise, unclear. This is better. Eating a 4-gram clove of raw garlic per day, 6 days a week for 6 months, lowers average low-density lipoprotein cholesterol in most adults with mild hypercholesterolemia. That's more precise, more clear. Precise is also said of a process or test or observation when it yields the same results over and over. So a precise test is one that's repeatable, consistent, but it may not be accurate. So we're going to focus on this sense in science. When we say that a process or a test or an observation is precise, what we're saying is it's repeatable, consistent. So precise is the same thing as reliable. Sometimes precise means exact, sometimes it means consistent. In science, go with consistency or repeatability. But a better word is reliable. Again, we're going to use the terms valid and reliable. We need to distinguish the ordinary and the logical and the scientific sense of precise and valid. Even scientists use these terms ambiguously, unclearly. In science, if we say a test of a proposition is valid, then we are saying it is both accurate and reliable, true and consistent. It's accurate because it reveals a true value. It's precise because it yields consistent, repeatable results. All valid tests are reliable or yield repeatable results, but some reliable tests are not valid when they produce inaccurate results. Now, good evidence should be accurate and precise. Accuracy refers to how closely a measurement or observation comes to measuring a true value. But measurements and observations are always subject to error or bias. Precision refers to how closely repeated measurements or observations come to duplicating measures or observed values. A better term to use is reliable. Thus, a reliable measure or test produces consistent measurements of the same quantity after repeated measurements. For example, a trustworthy scale or thermometer is reliable. A valid measuring instrument measures what it is designed to measure. For example, breathalyzers and blood samples are accurate and reliable, so they are valid. My advice, summarizing here: use the term precise to mean exact or clear. Use the term reliable to mean consistent, repeatable. Use accurate to mean true or close to true. Use the term valid to mean either accurate and reliable, as it is used in science typically, or the way we use it in logic or philosophy, it means a truth-preserving deductive argument form. I'll get to this later. Don't use valid to mean true, not ever. Just say true or good or credible or whatever you really mean. Recall the urine dipstick test. Suppose the dipstick indicates pregnancy. The dipstick says, "I'm pregnant." By scientific standards, home pregnancy tests can be accurate, produce a true result, but not reliable. They can be inconsistent, or not as reliable as other tests, for instance, the HCG blood test. Home pregnancy tests are usually valid, accurate, and reliable when people follow instructions, but they are not as valid as clinical tests. They're not as accurate. For example, an HCG blood test or ultrasound image is even more precise. But even the human chorionic gonadotropin blood test may be inaccurate. You can have a high HCG level if you have an ectopic pregnancy, a pregnancy which develops in some place other than in the uterus, in a place where it can progress. You can have a high HCG if you have a miscarriage, no longer pregnant. High HCG in the blood can indicate testicular cancer in men, tumors, ovarian cancer in women. Notice that the urine dipstick test cannot be a valid test for a male or postmenopausal female. This is what some of these look like. This shows you what some invalid results look like. No test of a hypothesis or research study is perfect. All findings are vulnerable to error due to either chance factors, random error, or observational measurement factors, non-random error. So let's review two sources of error in measurement. There's random error and non-random error. Random error is due to chance factors or variables and is often unknown or predictable. For example, each time you weigh yourself over the course of 5 minutes, the reading on the scale is different. What if that happens? Some kind of error has entered the process. You minimize this by taking more data points and taking the arithmetic mean. Randomness affects precision or reliability. Non-random or systematic error is due to unrepresentative sampling or a malfunctioning instrument or brain. Such error affects accuracy. Now, one form of non-random error we know by the term bias. If you want to know the temperature in a room, the ambient temperature in a room, you can't trust a thermometer when it's in direct sunlight. The sunlight biases the reading, biases the accuracy. Bias in a person might be their presumption that race corresponds to socioeconomic status or IQ. And so this is going to compromise any sort of measurement of a person's problem-solving ability. Psychological biases are huge issues because they are hard to detect and control. Racism, sexism, chauvinism, these are bias-based. So bias is a systematic error. It's not random. Bias is a systematic error that compromises accuracy. Basically, anytime you move farther from the truth in your measurement or your inferences, conclusions, bias happens. Bias is error, and it causes error. Again, error is the difference between the true value of a measurement and the recorded value of a measurement. The difference between what's real and what's observed. There are many sources of error. It can be random due to chance or systematic. Only the systematic kind is called bias. Random error, variability, and precision affects reliability too. It can be overcome by increasing sample sizes. Bias is not random. It's not enough to call an observation or assumption biased and then dismiss it. You have to show why it's erroneous, why it's biased, how that bias is enough to compromise measurement. For example, you need to show that an instrument is miscalibrated. It might be, but you have to show that it is, right? The assumption is that it's not. You're doing the measurement. You've calibrated your instrument prior. The scale has been consistent in the past, and now when you use it, you're getting strange answers. Possibly bias, possibly something else, possibly something systematic bias, possibly random error. How? How do you do this? How do you control for this? You demonstrate how a measurement or description is inaccurate, misleading, or false by showing where exactly it's making the mistake. Bias erodes accuracy, and so the validity of a test gets compromised. So there's accuracy versus precision. I've talked about this. Accuracy refers to how closely a measurement or observation comes to measuring a true value. Since measurements and observations are always subject to error, you get close to the truth. We want to reduce bias to get better accuracy. Precision refers to how closely repeated observations come to duplicating measured or observed values. Here we want to reduce the spread of values so we can become more precise. Okay, get closer to the truth. Summarizing, valid and reliable measurements increase the accuracy and precision of descriptions. A sample represents a population accurately if the sample statistic is equal to the population parameter. Error always exists when the sample statistic and the population parameter differ. It can be systematic or random. Error in sampling is systematic when there is a flaw in the sampling measuring procedure. Bias is systematic error that results from a flaw in the sampling design, such that some elements of the population are omitted or overrepresented. Sampling error can also be random. This is not bias. Chance variation influences outcomes of random selection procedures, even when we increase sample size. I'm not going to go into all these statistical sources of error here. I want to mention the difference between a statistic and a parameter. A statistic is a characteristic, a property of a sample. A parameter is a characteristic, a property of a population. In order to understand populations, we draw samples. We make statistical claims about the samples so we can draw conclusions about the larger population, the whole population. All we can never do in a population is observe a part of it, and we project from the part we observed onto the whole thing, and this is where error can creep in. Here are some common sources of bias. Systematic reviews try to control for these, but they can still occur. Selection bias. This is when compared groups, experimental and control, may differ undetectably in baseline characteristics. So you need to randomize your interventions, randomize your assigning of people to different groups. Performance bias. This is when differences between groups in treatment or in exposure to factors other than the interventions of interest emerge. When people say, their status, they know whether or not they're getting a drug or a placebo. So blind, masked participants and investigators are better. Detection bias. This happens when differences between groups in how outcomes are assessed skew data. For example, different diagnostics produce different results. Also, sometimes differences are artifacts. Attrition bias. Withdrawals happen from studies. This skews results. People are dropped out of studies. They no longer want to participate. People die. Adverse events occur. There is also reporting bias. This is big. This happens when only statistically significant results get reported. If we don't report the results that are boring, that are not supportive of a hypothesis, that are not statistically significant, we get only a one-sided view of results. In fact, Dr. Ben Goldacre finds much of this goes on in the positive findings we find in published research. Positive findings are around twice as likely to be published as negative findings, and this can exaggerate the effect of whatever it is you're testing. This is a cancer at the core of evidence-based medicine. Every day there are news reports of new health advice, but how can you know if they're right? Watch Ben Goldacre's video, Battling Bad Science, to see some of the disturbing ways that accuracy and precision get compromised in research. Doctor and epidemiologist Ben Goldacre shows us the ways evidence can be distorted, from the blindingly obvious nutrition claims to the very subtle tricks of the pharmaceutical industry. This is a TED Talk. Look for it online. It's called Battling Bad Science. Let me just summarize some of the reasons that papers are rejected for publication. Papers don't pass peer review. Perhaps the study itself doesn't pass the review of fellow experts. And there's lots of ways, lots of good reasons for papers not being published. A paper can be badly written, can be incomprehensible. Perhaps a study did not address an important scientific issue. Maybe the study's not original. Someone else has done a similar study. The study doesn't actually test the author's hypothesis. This actually happens a lot. A different type of study should have been done. There are these practical difficulties, for example, recruiting subjects, which leads authors to compromise on the original study plan protocol. Sample size too small. Study was uncontrolled or inadequately controlled. In fact, we often see the results of observational studies, our own observations, compromised by the fact that we don't have any controls. We are not controlling for biases. We're only counting the positives, not counting negatives. Statistical analysis can be incorrect or inappropriate. That's a big one. This is why you have to have 1 or 2 or 3 statisticians involved in your studies. Authors draw unjustified conclusions from their data often. There can be conflicts of interest. Authors or a sponsor might benefit financially from publication, and insufficient safeguards are in place to guard against bias. Nevertheless, one can benefit and do good. Let me mention one more, the weird science bias. Social psychology relies heavily on weird subjects. Very often college students, but they don't represent most people. Weird stands for Western, educated, industrialized, rich, democratic countries. Weird subjects from countries that represent only about 12% of the world's population differ from other populations in moral decision-making, reasoning ability, fairness, even visual perception. Weird people, for instance, are better at optical illusions involving line length. All right, that's enough for now. The next module, Module 3, will be about scientific reasoning. And for that, you need to read Chapter 2 in the Akasha text and Handout 2 in Canvas, Module 3, Truth and Knowledge. We're going to talk about truth and knowledge first. In order to understand what scientific knowledge is, we need to have a notion of truth. Also, for next week, the following week, I should say, watch the video, The Vaccine War. Also, you need to watch the video, The Vaccine War. There is a link to it in Canvas Module 3. Be prepared to answer the following question. Lots of people conclude that vaccines are unsafe for their children. What are their most compelling arguments for this belief? You should be able to state at least one of these arguments fairly and concisely. This is the end of the slideshow for this week.